So, welcome everybody to this course of the Advanced Atomic and Molecular Physics course by Andreas Hauser. My name is Markus Koch. I'm Associate Professor at the Institute of Experimental Physics. And today in this lecture, I'm going to talk about two topics. The first topic will be quantum optics, and here in particular laser cooling, which is a particularly exciting branch of quantum optics. And the second topic I'm talking about is ultrafast laser physics. Now, the reason I'm jumping in for my colleague here today is that I'm somewhat experienced in both experimental techniques. So quantum optics was a research field at our institute for quite some time ago, although, and I was only partly connected to this topic during kind of my diploma thesis, I would say. But the second topic, ultrafast laser physics, is my research field I'm pursuing now, and I'm gonna talk in more detail about this. But let's get started now with quantum optics and laser cooling. And in order to talk about this, we have to take a closer look to the. Okay, sorry, let's just turn the laser point on. We're gonna take a closer look on the processes, rather simple process of photon absorption and emission by atoms, yeah. And the point is now, up to now, I guess you have been concerned in this process mainly by the conservation of energy. So a photon of photon energy h nu is absorbed, the atom is in excited state, and eventually after some time it will emit and emit a portion of the same energy. Yeah? In order to use this process so this is the fundamental process of laser cooling, but in order to describe this properly, we also have to look at momentum conservation. Yeah? So we also have to account for the momentum the photon carries. So this will give a push on the atom because the photon is kind of absorbed, annihilated, and therefore a still standing atom will be moving to the right, in this case afterwards, after photoexcitation, and after the natural lifetime after emitting a photon, this photon will, with energy h times nu, will also carry a momentum h bar k, and therefore giving another push upwards in this case. So with some actually the emission momentum is pointing in this direction, and after the absorption and emission process, the atom will be moving at this direction. So the momentum of the atom will change. Yeah? And so this was for a still standing atom initially, and if you use this or apply this in a clever way, you can also imagine that you can actually slow down, decelerate atoms, and that's what we're gonna talk about in laser cooling. Yeah. So if we take a closer look at this momentum, the trick now is to use it for deceleration. That absorption always is in the same direction because the laser beam is coming from one direction. So this is given or set by the laser beam propagation direction. And if this is counter propagating to the movement direction of atoms, yeah, then you immediately see that after absorption, the initial momentum of the atom is reduced, yeah? And then the important point to be considered here is that the spontaneous re-emission is randomly distributed in all angular directions. Yeah. So after all, as you can see here, after the absorption and emission cycle, the length of this momentum vector has decreased, so the atom is slowed down. Yeah. So the trick here is always that you do the absorption always from one direction, and having the emission randomly distributed in all spatial directions. Yeah. So with this, you can understand that you have a net momentum decrease within one absorption emission cycle, and doing several cycles, we can actually significantly decelerate atoms. Yeah? Let's also look in the energy picture on this. So the question, there's still one more trick to be applied, and this can be understood in this energy description. And this trick is that you are working with detuned photons. Yeah. So meaning, so this is explained in this images on the right side here. Let's start with the second image here. So this will be from the reference frame, from the lab frame. Yeah. So you have an atom moving to the left and a laser beam coming from the left moving to the right, which is a red color. Okay, so let's assume this is kind of probably, I don't know, 700 nanometers or something. Yeah. Now if you move to the atom, so the moving reference frame in picture 1 here, the atom actually sees a blue shifted photon, a blue shifted wavelength. This could be green, I don't know, 500 nanometers or so. And this is because the atom is counterpropagating to the laser beam. So you have to consider Doppler shift and can understand that the atom sees blue shift at a lower photon energy, yeah, a lower wavelength, lower photon energy. Okay, so again in the laboratory frame, you would say the atom absorbs a red photon, a low energy photon, yeah, but then it re-emits in the lab frame a higher energy photon. Yeah, if this is so, if the atom is moving, for example, to the right afterwards, you get a blue shifted, even a blue shifted photon with respect to the excitation wavelength. So the excitation wavelength, the transition wavelength is green, as you see from the moving reference frame. If it now emission, for emission it depends on whether the emission is in forward direction or in backward direction. Yeah, but again, sorry, this was too quick. But again, it's randomly distributed, so sometimes it will emit yet a higher photon energy, sometimes it will emit lower photon energy. If emission goes upwards, it will emit a green photon. Yeah, so on average, a red photon will be absorbed, and a green photon will be emitted on average. Yeah? So again, here you can understand that, or from this picture you can see that this slowing down of the kinetic energy of the atom comes from absorption of a lower energy photon and emission of a higher, on average, higher energy photon. Yeah? So in this you see that both actually momentum conservation and energy conservation are fulfilled. Okay, so let's put some numbers to this. One type of atom that has been, I think this was even one of the first atoms that have been cooled down in traps, as we will see, are alkali metal atoms, sodium atoms, for example, because the electronic structure is rather simple. You can, and they have favorable excitation wavelengths, so you can easily build lasers because this is in the near infrared. So you have plenty of lasers available there. And now if the recoil velocity for sodium atoms, for example, is 3 centimeters per second, this means if this refers to this first process here, if an initially still standing atom absorbs and re-emits a photon, it will move afterwards at 3 centimeters per second. Yeah, this is not much of a velocity, rather slow, but you know, the natural lifetime is in the nanosecond range. So an absorption emission cycle takes only a few nanoseconds, probably 10 nanoseconds or 20 nanoseconds. So you can drive rather a lot of these absorption emission cycles if you have sufficiently high photon energy in your laser beam. And if you just put, okay, don't go to the extreme, to 10 to the 9, you can do something like, I don't know, 100 times 10 to the 8, 10 to the 8 cycles, but let's say, okay, 3 times 10 to the 7 absorption emission cycles per second. This gives an acceleration of 10 to the 6 meters per second, so it stands still rather quickly. So this is really this light force kind of. It's actually kind of a force because an acceleration. The atom has a mass, so you can connect a force to that, and this deceleration force, the force due to laser cooling, can be rather large, as you see here. So let's go one step further on this slide. Sorry, fighting with my laser pointer. Let's go to Doppler cooling. So this is one step further to the real setup now. So we're considering two laser beams counter-propagating now, and we're looking at this force we just have talked about as a function of the velocity. Okay, so let's keep in mind that we're not looking. This is not the spatial coordinate, but the velocity we're looking at. Okay, the spatial coordinate comes on the next slide, which requires an external magnetic field, as we'll see. But for the moment, we only have these two counter-propagating laser beams and look at the force as function of velocity. Since the two counter-propagating beams are red detuned to the red, to lower photon energy with respect to the atomic transition we use for laser cooling, we see that, for example, here, that the atoms that move to the left, so counter-propagating to this laser beam, they will be excited and or undergo this excitation emission cycles and the connected force at the maximum if the velocity corresponds to the detuning. Yeah, and because the laser beam has also line width, we have actually this shape. Yeah, so photons that are too slow, they are not exactly resonant, but due to the spectral width of the laser beam, there is some light, but at lower intensity. And they will experience a force, but a lower one compared to those at resonance, and correspondingly for faster atoms. Yeah? And the same is true for the right beam. So atoms moving to the right, positive velocity, will counter-propagate to this right laser beam and experience the same force, although in the opposite direction, to the left side. Okay. So what we have here is really a velocity dependent force. Yeah. So atoms moving rather fast to the left experience a force that pushes them to the right, and atoms moving to the right will experience a force that pushes them to the left, so or decelerates them, one has to say. Okay, and it's important now to realize that there is no spatial dependence. Yeah, so the atoms will eventually drift out of the laser. So the laser beam diameter can be 100 micrometers or a millimeter or something. Yeah, you typically use rather focused laser beams here, and so the atoms will eventually drift out of this interaction volume. But during the interaction time, during their presence in this laser beam volume, they will be cooled rather efficiently, as we've seen before, and reach temperatures on the order of the microkelvin range. So this is what's called the Doppler limit, because this is the lowest kind of the lower temperature limit that can be achieved with this Doppler cooling. Okay, so again, no spatial dependence yet, but this detuning counterpropagating laser beams already allows you to reach a relative low temperature, low particle velocities. So the question is now how to really achieve this spatial dependence. How can we now really kind of trap these cold atoms and keep them trapped in a small volume in space? And the resolution, or the solution to that, is a so-called magneto-optical trap, a MOT. So in a way, the counterpropagating laser beams with Doppler cooling we had before can be seen as optical trap. Yeah. So this is also the case here, only for 6 laser beams. So we have, so this will be the center here on this right hand drawing. The center beam will be, or the center volume will be where the cold atoms are trapped. So there is where the cold atom cloud will be located. And to apply this laser cooling, this Doppler cooling into any direction of the moving particles, the moving atoms, we have to use 6 laser beams. So we have one counter-propagating laser beam into X, Y, and one into Z direction. Yeah. So typically you have one laser beam which is retro-reflected by a mirror 3 times the whole thing. Yeah. So this gives an interaction volume of probably a cubic millimeter or a couple of hundred cubic micrometers in the center. Okay. And in addition to that, to now induce this spatial dependence, we use a magnetic field, therefore mod. This is the M in the mod, and these are anti-Helmholtz coils. Yeah, these are arranged around this volume. So these are the 2 blue circles here, and you know probably Helmholtz coils. So a pair of Helmholtz coils is this is probably drawn in this lower image in a better way. Helmholtz coils are typically 2 coils that are at a distance of roughly their diameter, and if so, you can produce a rather homogeneous magnetic field. Yeah, this would be Helmholtz coils, and anti-Helmholtz coils is the same thing, but you have just counter-propagating current direction. So one is in one coil the current is clockwise, in the other coil it's counterclockwise. And with this, you can easily see that, sorry, this was too quick, that you have a zero field point in the center, and moving into any direction out of this zero field center location, you are going to increase, or the atoms are going to experience an increased B field. Yeah? So if you want to draw the B field lines, which is in red here, somewhat unusual, typically B field lines are green, but here they're red. And so you see that you have this, like, they would come into the volume in between from in between the coils and leave the volume through the coils here because of clockwise and counterclockwise current directions. Okay, so here is this center point zero field direction spot in the center of the volume. Okay, now this point also has to coincide with the laser focal, with the laser foci. So typically the laser beams are focused, and now you can play a trick in order to make use of this spatial dependence, and this is the Zeeman effect. Yeah, you know from your lectures that the Zeeman effect is this spatially dependent energy level shift. Yeah, and this is the effect you make use of because you would have kind of zero or no energy shift in the center, but as the atoms move, and no matter in which direction they move out of the center, there an energy level will be increased, and this is used in a clever way to tune the laser beam into resonance. Yeah, so atoms that are standing still in the center experience no force, but as soon as they move out of the center, they enter regions of stronger Zeeman shift, energy level shift, and therefore they would come into resonance with the laser beams and are pushed back into the center again. So this is the function principle of a magneto-optical trap. So exactly this spatial force dependence, which is zero in the center. Yeah, and the concept sounds rather simple. Nevertheless, the experimental realization was definitely not. So this was awarded the Nobel Prize in physics, I believe, in 1979 by Chu, Cohen-Danucci, and Phillips. And this really was the entrance to, like, entering this cold, or kind of proceeding strongly towards this cold atom physics, yeah, cold clouds, and was the first very important step towards Bose-Einstein condensation, which we are going to talk on the next slide. that I wanted to say. If you want to proceed, so again, this would bring it down to 100 microkelvin, to the 100 microkelvin regime as before, because the cooling effect is Doppler cooling. Yeah, just by adding the spatial dependence, you don't gain cooling power, so you would not be able to reach lower temperatures. Yeah, so there are additional cooling processes required, and these are evaporative cooling, and which are done by magnetically trap only, so by switching off the laser beams, and with that you're gonna reach about 100 nanokelvin, so in some 10 nanokelvin range, which is then sufficient to do the or to reach the Bose-Einstein condensation, which we'll talk on the next slide. Concerning Bose-Einstein condensation, or short BEC, we have to look once more at the temperatures. So for 100 microkelvin atomic cloud, so an atomic cloud after laser cooling at a temperature of 100 microkelvins, the particle velocity is, although it's rather slow, is still in the meters per second range, like 0.1 meter per second. And at these velocities you still have classical behavior of the particles, of the atoms, because the associated de Broglie wavelength is on the order of the atomic diameter. Yeah? So a particle is still a particle, a classical particle, and if you look at them, at particles in a box, they kind of behave like billiard balls because they undergo scattering, but do not show any quantum behavior. Yeah? This significantly changes if you further cool down. So for 100 nanokelvins, for example, so 3 orders of magnitude colder, the Broglie wavelength becomes on the order, or is larger, significantly larger than the atomic diameter. So the particles have to be treated as wave packets in this case, yeah, so quantum mechanical objects, wave packets, and this is fundamentally different, especially if you further cool down, and for lower temperatures, the wave functions start to expand, of course, because the momentum decreases, so an increasing the Broglie wavelength, and that's to a point where the wave functions start to overlap. So at the critical temperature, which is the transition temperature, the Bose-Einstein condensation, the overlap of wave functions becomes so significant that many particles are actually in the ground state. So it's not, so we say that they condensate into the ground state, into a giant matter wave. Yeah? So this clearly requires bosons, bosonic behavior of particles. So integer total angular momentum, and if this is the case, they are all in the ground state. They are allowed to be in the ground state because after all they're bosons, and the matter waves overlap, and the whole atomic cloud starts to show some collective behavior. Yeah, eventually at t equals 0, which is not reachable, of course, all would be condensated in the ground state, but typically at below the critical temperature, some particles are in the condensate and some are still moving around. Yeah, so typically you would have an atomic cloud of some 100,000, some a couple of million atoms there, which is a macroscopic object, so probably a cubic millimeter or so of volume, which can be photographed and investigated. And this started a whole new field of research, a whole new research branch, because this quantum mechanical object could be studied now. Yeah. So people asked questions: how can you photoexcite such systems? How does this systems accommodate angular momentum? Of course, also angular momentum must be quantized. These are vortices then, and so on. So this triggered a whole new research branch, and the first experimental realization of a BEC was in the, I forgot the number, in the late 90s, I believe in 1998 or something. And for this, this was done by two groups kind of simultaneously, and three people were awarded the Nobel Prize, namely Eric Cornell, Carl Wyman, and Wolfgang Ketterle. And already in 2001, so pretty quickly afterwards, and this shows that a whole new research branch was made available by this, and this is actually a field where Austria is quite on top, kind of. So the Innsbruck groups of Rudi Grimm and Hans Christoph Nagel and co-workers are really big players in this game. Yeah? If you want to read more, I think the Ketterle group at MIT has a very nice web page, and Wolfgang Ketterle is a very he visited our institute some couple of years ago, and is really able to explain this on a very basic language, easy to understand. So go and watch his webpage if you want to learn more. Okay, so with this I'm done with Bose-Einstein condensation and come to my next topic.